Okay, we're going to do a little bit of review of polar coordinates here. There's a lot of things going on in this one page, and a lot of little things that we can review. You see it says find the horizontal and vertical tangents of the graph. Of course, horizontal and vertical tangents, these are places we need the derivative. Well, let's start by just reminding ourselves that in polars, x is equal to r cosine theta, y is equal to r sine theta. That is the key. Now, almost any time I am faced with a polar problem that maybe doesn't require area you don't really need to think about this, but anytime I'm confronted with a polar problem, I would usually just write that somewhere so I remember it. So in this case, r is, I'm going to get rid of the parentheses, 2 minus 2 cosine theta. Okay, so let's just write this. X is r. Well, again, here's what r is for our graph. So it's going to be r multiplied by cosine theta. And y is equal to r multiplied by sine theta. Okay, make sure you see where that came from, right? X is always r cosine theta, so r for us was 2 minus 2 cosine theta. So it's just substituting what r is equal to for our general case. So to find the derivative, we need dy d theta divided by dx d theta. Okay. So let's start with y. We're going to need product rule. So we're going to have first multiplied by derivative of the second plus the second multiplied by derivative of the first. Okay, on the bottom we're going to have dx d theta. So again we have first multiplied by derivative of the second plus the second multiplied by the derivative of the first. Not pretty. Okay, there's a lot in here. Now, of course, for a horizontal tangent, if we want to think about it this way, a horizontal tangent, we need dy d theta, the numerator, to be 0. Okay. For a vertical, we need the denominator, or dx d theta, to be 0. Now, certainly you can see there are these spots. Here we definitely have verticals. Right over here. We definitely have some horizontals, right? Maybe even down here, right, as it comes to 0. So we definitely have these spots in the graph. Well, here's the tricky thing, and let me kind of just shrink this graph down so I can bring this down. Looking at when dy d theta is 0, looking at where this numerator is 0, this is not something you would be expected to solve by hand. So what I did was I graphed it. Okay, so let me bring this down. Okay, let me show you the graph. Here it is. Okay. So what you see here is just dy d theta. I really just graphed it in Cartesian. I just went to my y equals on my calculator in just old function mode, and I graphed it, and I figured out when it was 0. Well, 0, 2 pi over 3, and 4 pi over 3. And I had them just as decimals, but it certainly would work. So theta was 0, 2 pi over 3, and 4 pi over 3. It was also 2 pi, but of course that's just kind of going back to where we started. So this, what this did for me was it gave me you know, you actually gave me those values. This wasn't really something I could have done by hand. Feel free to go back and just graph them to find zeros. You know, all I needed to do was figure out when this whole top equation was 0. I just put it in my calculator, graphed it from 0 to 2 pi, so because that I figured was one full you know, revolution around the graph, and that was it. So the next thing I needed to do, of course, was the same thing for the denominator. So let me show you that one. Okay, here it is. So for this one, theta was 0, pi over 3, and 5 pi over 3. Okay, and again, I just went into my y equals, and I typed this whole thing in, and I graphed it to figure out where the zeros were. Okay, I didn't leave it in polars. I just graphed it in regular function mode. Now, there are a couple things to just pay attention to here, and I mean, I think we're pretty much done with this this problem, but I wanted to, if I can, expand this out. Okay. Some things I just want you to kind of pay attention to. First of all, you'll see that 0 appears in both. And that's because as it comes down here, it actually stops. You know, it starts right there, it comes back right there. So there is kind of this vertical piece because the graph doesn't continue. So we're not wrong in saying there's a vertical asymptote there, but we're also not wrong in saying there's a horizontal because it begins by being, for an instant, horizontal. Now to actually get those coordinates, you know, if you said, well, I actually want to know what the values are. And this is where I think it's so important to write down what I wrote down right away, this little stuff in the bubble. Because I will always have people say, well, okay, now I know the angles, but I don't know how to actually get the coordinates. Well, what you'd have to do is you'd have to take 0 and plug it in to what x is equal to. 2 minus 2 cosine of 0 multiplied by cosine of 0. And 2 minus 2 cosine 0 sine of 0. Well, that comes out to be the point 0, 0. Okay, so that will give us this first one. Plugging in, you know, theta equals 0 gives us that first part. Now 2 pi over 3, when you plug that in, then you'll get this coordinate. You know, when you plug in 4 pi over 3, then you'll get this coordinate. But you'd actually have to plug them back in to what x and y are equal to in order to get the actual coordinates. All right? Because, of course, at this point we know what the angles are. And a lot of time that's enough. A lot of times the AP exam will have you stop there. It was a lot of work just to get there. But it's certainly possible to get the coordinates, and actually fairly easy once you've gotten the angles. Okay. Again, don't feel like you needed to get the angles by hand. There was no way I would have expected you to solve this and get 2 pi over 3 and 4 pi over 3. Okay? This is a pretty tough example with a lot of things in it. I'm going to really quick remind you of the area formula after this, but this is a big one. Remember how to do the derivative. Okay, that's what I really wanted to focus on. I just kind of liked all the things that came into this problem. So here, find the area of the region lying in the inner loop. Well, remember, area of for polar is always 1/2 integral of r squared d theta. So we have a lot of information already. We can do 1/2 the integral of 1 minus 2 sine theta squared d theta. Okay, so now all we need to do is figure out, okay, here's the inner loop. What two angles enclose the inner loop? Well, remember, r is a measurement of how far away from 0 you are. Well, the inner loop starts at 0, 0, so in both those cases, r is 0. So let's do this. Let's say, okay, 1 minus 2 sine theta equals 0. So 2 sine theta equals 1. So sine of theta is 1/2. Okay, so now you got to think, well, where does that happen? Where is the sine of theta 1/2? It's pi over 6 and 5 pi over 6. And those are our bounds. That's it. Okay, that will give us the area. And we would certainly just type that into our calculator. I wanted to point out, because so much of this exam and so much of what we do with polars, we use FNint on our calculator, but please notice that if you expanded this out and used some of the double angle identities and Peel method that we learned, you could do this by hand. Okay. All right, next, find the area enclosed by one petal of the curve. Okay. Well, again, we're going to have, I always just start with this, 1/2 r squared. Don't forget that formula. That's so important, okay? Now, you'll notice that, again, one petal, I mean, it starts at 0, or you know, that's what we need to enclose is this, and at that point r is 0. So let's again start by just saying, okay, 4 cosine of 3 theta is 0. Well, that means the cosine of 3 theta is 0. And you could do some solving for this. You could say, well, the cosine is 0 at pi over 2, and, well, negative pi over 2, but this would be dividing that by 3. So your bounds, you could go negative pi over 6 to pi over 6, because I'd have to divide by 3. Remember, you know, let me just write this down. The cosine of pi over 2 is 0. Well, that means that 3 theta must be equal to pi over 2. There are other ways you could have done this. You could have gone from 0 to pi over 6 and then taken the 1/2 out. You know, 0 to pi over 6 would have just given us this. And then you could have just multiplied the entire thing by 2 or dropped the 1/2. The entire thing is traced from 0 to pi. You could have done that and then just divided it by 3 at the end. So lots of different ways to set this up.